The aim of this lab was to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on a spring. We obtained position data from a video using Tracker, then we constructed a computational model of the motion using VPython. We compared the predicted and the observed motion and plotted the energy changes predicted by the model. We found that the energy principle was satisfied, and that the predicted and observed motions followed the same pattern, however were not exactly the same. First, we obtained position data from a video using Tracker. The origin was set at the attachment point of the spring, with the mass hanging in the negative y direction, and the positive x-axis pointing towards the right. The measurements were calibrated to the distance between the fixed attachment point to the mass hanging motionless on a spring, which was 0.7 meters. I tracked the point masses at the center of the object as it oscillated. I saved the x and y positions into a CSV file so that they could later be used in the model when comparing the observational and the predicted motion. This is the formula to find the period of oscillation t, and using observations from Tracker, we found this to be approximately 1.524 seconds. We rearrange and substitute t and the mass of the object into the formula to find the spring stiffness, K sub s, which is 6.83 newtons per meter. We noted at the start of the video the object is hanging motionless, which means that it is in static equilibrium. Therefore, the gravitational force and the spring force are equal. We rearrange and substitute in to find the relaxed length of the spring, which is 0.123 meters. This is the model. Observations from the video provided the initial conditions of the object, so its initial position and velocity. Since the object is released from rest, we know that the initial velocity is 0. These are some of the other values I initialized in the model. The L vector gives both the length and the orientation of the spring. The L vector points from the attachment point to the location of the mass. In this code, the variable spring.pause is the location of the spring attachment point. The unit vector L hat describes the direction of the L vector. S describes the stretch or compression of the spring. Newton's second law is used repeatedly in this loop to predict the velocity and the position of the object as time advances. This model assumes that the drag force is negligible, so the system, which in this case we took to be the mass only, was being affected by two forces from the surroundings: the weight force, due to the gravitational force from the Earth, and the spring force. Therefore, we have set the net force as being equal to the sum of the weight force and the spring force. F gravity acts only in the y direction, so that is why its x and z components are 0. These lines of code update the spring force, which is necessary because as the mass moves and the ball position changes, the spring force changes. This line updates the visualization of the spring. In these lines of code, we read the x and y positions of the observed mass into the Python program. These are from the CSV file we saved earlier from our tracker analysis. When using the energy principle, we chose a system consisting of the mass, the spring, and the Earth. The change in the total system energy is equal to the sum of the energy changes inside the system. The change in the kinetic energy of the mass, the change in the gravitational potential energy, and the change in the spring potential energy. Here in the code, we compute the system energies before the program enters the loop. These are the formulas which specify the energies, and this is their equivalent in Python code. In the while loop, we specify the energies at the start of each iteration, beginning with the initial energies when the time is equal to 0. Here, we compute the final energies for the system, and this allows us to find the energy changes. Now we run the program. The blue ball represents the predicted position and the red represents the observed position. We see that the weight force represented by the black arrow is always pointing down, and the spring force in blue is always pointing up, meaning that the spring is longer than its natural length. The weight does not change in magnitude, but the spring force does. The arrow representing the spring force is getting longer and shorter as the mass oscillates. The comparison between the positions is not that bad. This graph plots the predicted and observed y positions. The predicted position is in blue and the observed position is in red. They match quite well. When analyzing the data in Tracker, in some frames the object was blurred, so I might not have been able to pick the exact position of the object, and this could be why the observed position of the mass may be different from the predicted. The model assumes that the drag force and the mass of the spring is negligible, but drag force was present, and the spring did have a small mass in the real-life experiment, and these could be further reasons why the observed and the predicted positions differ. This graph plots the energy changes. The blue line represents delta K, the red is delta U sub S, the green is delta U sub G, the yellow is delta E total. We see that the energy changes oscillate. The changes in the gravitational potential energy and the spring potential energy oscillate with the same period, and these two energy changes are approximately the same size but are opposite in phase, meaning that when one increases, the other decreases. The changes in kinetic energy are also both positive and negative. The mass gains and loses kinetic energy. The kinetic energy change oscillates twice as fast as the potential energy changes. The sum of all these energy changes is the yellow line, which is zero, just as expected based on the energy principle. What does this mean? In our model, we considered the mass of the spring as negligible, so there were no contributions of the spring to the change in kinetic or gravitational potential energy. The interaction of the system via the attachment point to the spring does not transfer any energy because the attachment point undergoes no displacement, therefore there is no work done and so no energy transfer. We chose to include the Earth as part of our system, and there were no surroundings. Therefore, the energy principle states that the total change in energy should be zero, because there were no interactions that transferred energy to and from these surroundings, if we neglected small effects like the air resistance. The energy graph shows us that the sum of all the energy changes in the system was equal to zero, which means that the energy principle was satisfied. Using the data we obtained from Tracker, we were meant to make two separate estimates of the oscillation period, one from the x position data and one from the y position data. These are the oscillation periods I found. The y is a little bit smaller. The periods of oscillation for x and y should not be the same, because the mass swings in the x direction in a pendulum motion, whereas it moves up and down in the y direction in a spring motion. The two different types of motion are calculated in a different way, therefore it is expected that they should be different. Thank you very much for listening.